All right, guys, we finished up with low mass star death. We talked about red dwarfs and stars up to 8 solar masses. We talked about type 1a supernova, garden variety nova, but now we got to talk about high mass stars and how they die. That would take us on to page 83. So, page 83, high mass stars. So these are stars greater than 8 solar masses. When they get to the end of their life, gravitational pressure collapses the carbon-oxygen core. Recall that in that carbon-oxygen core, it's being supported by degenerate electron pressure. And in this case, the gravitational pressure exceeds the back push of the electron degeneracy. All right, so we're getting into the Chandrasekhar limit again, only this time, this is occurring within the star itself. So what happens? Well, if you're going to get this kind of a collapse, then you're going to get pressure. When you get pressure, that's going to raise temp. Okay, that temperature should be familiar to you by now. That's the magic temperature to trigger carbon fusion, all right? And that yields neon and magnesium. The collapse continues. With that collapse continuing, the pressure continues to increase. That increases temperature even further. Now we get up to 1.2 times 10 to the 9th kelvins. That's 1.2 billion kelvins. At that temperature, we get neon fusion. Neon fusion yields more oxygen, more magnesium. It doesn't stop. At 1.5 billion kelvins, we get oxygen fusion. That yields sulfur. Silicon. Phosphorus. It continues on. We get to 2.7 billion kelvins. We get silicon fusion. And the product of silicon fusion is iron. What is iron? The star killer. Iron kills stars. More on that in a few minutes. But let's just look at the timeline of how this works. When we have a large star, again, greater than 8 solar masses, it gets to the end of its life, and now we've gone through the triple alpha process in the core. The core has been converted into carbon. That means that the fusion stops. If the fusion stops, it cools. That means that we get compression, yeah? So that compression continues and continues and continues until we hit the magic number right there, 600 million kelvins. That triggers carbon fusion. Carbon fusion gives us neon, magnesium. It continues to collapse. More pressure, more temperature, 1.2 times 10 to the 9th billion kelvins. Neon fusion gives us more oxygen, more magnesium. Continues to collapse. 1.5 times 10 to the 9th kelvins. Oxygen fusion gives us sulfur, silicon, phosphorus. And these are just a few. This is just a rough outline of the elements that are created in this process. Finally, we get up to 2.7 billion kelvins. We get silicon fusion. Silicon fusion gives us iron. Iron is the star killer. More on that later. But now let's just look at the timeline. Carbon fusion. That tends to last somewhere around 600 years. And in astronomic terms, that's not a very long time, but yeah, 600 years. And then we get to the neon fusion. Neon fusion, that lasts for about 1 Earth year. Oxygen fusion. That lasts for 6 months. Silicon fusion. One day. 1 day. All right. This is pretty amazing stuff. The iron core does not fuse. Because there just isn't enough energy to trigger iron fusion. Does not fuse, does not emit photons. Recall, photons are the byproduct of fusion. So if there's no fusion, there's no photons. If there's no photons, there's no outward pressure. The core is supported by electron degeneracy alone. And as the iron deposition continues, that is to say, silicon continues to fuse and deposit iron on this core reaches the Chandrasekhar limit. .4 solar masses. That's the limit of electron degeneracy. It can't support any more mass than that. The Chandrasekhar limit is reached and the core collapses. That is to say, the iron core collapses. And remember, what happens with core collapse after reaching the Chandrasekhar limit? The whole thing blows. Next page.